Hello, everybody. I want to talk about ATP a minute because we keep mentioning in biology class, and every time I talk about ATP, whether it's my biology or my chemistry, I think back to whenever I was in high school biology class and my teacher tried to teach me ATP. I remember this lesson so well. He rolled in a movie, a video. We were all excited. We started watching this video, and we didn't understand a single. We knew it dealt something with energy. And he looked upon all of our faces after watching about 15 minutes of this video. He's like, nope, that's not going to work. And he took it and threw it away. Well, we're not going to do that today. I want to actually kind of talk to you about what's really going on here with ATP. I think it's really cool. It's so easy to not really understand it because we just say, oh, it's used for energy, or it is molecular currency, or it transfers energy. And you're like, okay, I get the words, but hey, come on, teach, what's really going on here? Hopefully, what I can show you today will help out just a little bit with that. I promise you, there are so many videos out there about how ATP is made, how it works with other things, and there may be some better ones. But I want to tie this into what I think may kind of link to what we've done recently in our class here at WAVA, and maybe make a bit more sense. And then if you want to go look at these videos elsewhere on Khan Academy and everywhere else about what ATP does, especially how it's made. ATP pumps are really cool. Do so. Kind of learn a little bit more about it. It's really, really cool stuff, and well, that's how we're made. So first off, here's a diagram of the ATP molecule. This thing's big. This thing's big. But what we're really concerned with is right here, these three P's right there. These are our phosphate groups right there. The phosphates right in the center. Over here to the right, this is important too. Really don't care as much right now about this. We'll talk about these things later on, especially we'll talk about DNA. But I made a model of just the phosphates. I wanted to make a model of the entire thing, but I ran out of parts. Here are just our phosphates. Every little of these purple things represents a phosphate ion, and you can see here, that they're also attached to oxygen. All these O's here are oxygens. Okay, all these O's represent oxygens. Now, folks, if you didn't know, oxygen, being something we kind of have to have, is the greediest, the meanest, the most unruly, one of the most unruly, atoms out there, and we have to have it. We cannot live without. Oxygen is a bully. It's always stealing things. It's always butting its way into where it doesn't belong. But it's why we're alive, because this stuff here is just so active. It does some amazing things for us. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, there's one I didn't even put there. There's like 10. 10 oxygen atoms with this series of three phosphate atoms. So this is impressive. Really, really impressive. ATP, as you remember, should know, is made by the process of cellular respiration. Cellular respiration is what we're kind of studying that right now. But we're just going to kind of start with the process. Okay, what happens? How does this crazy looking molecule here? How does it transfer energy? Okay, first off, let's go level one here. Level one. These sticks between this molecule here. When you look at the model here, or these sticks represent bonds. These little lines. Each of these bonds has a lot of energy built into it. Okay, and we're talking about cells. Energy, usually we're talking about heat. And so it takes energy to make these bonds. It takes heat to make these bonds. It also takes these atoms to run into each other, like demolition derby. So that's kind of like level one. Level two here, talking about just about the ATP itself and not our bonds here. So what happens is we got our ATP molecule. It was made by respiration. It is ready to go doing stuff, and hey, it's got all those oxygen there. This thing's unhappy. It's unhappy. It is shaking around. It's wiggling around. It's unhappy. It wants to become more stable. It wants to go do something. So as soon as it has the opportunity to do something, it's going to. And it's going to fast. Super, super, super fast. So we get a water molecule coming by. And the water molecule does what it does because it also has lots of oxygen in it. It's going to come by right here and it's going to smack it right there. Go boop. And it's going to rip off one little phosphate. And now we have this thing here called ADP, diphosphate. There's two. And it's going to go float away and it's all lonely. It's going to try to find a new friend. But now this phosphate here, this phosphate's going to run and do stuff. This thing is super shaky. This is like you've had too much Red Bull and Monster and sugar all in the one, and you got the super jitters. You got to do something to get rid of all this extra energy. It's going everywhere. Well, it's going to go do something. Okay, it's going to do something, and it's going to find some other molecule, some other compound, something else, and it is going to smash into it as hard as it can. It's going to cause stuff to happen. Okay. And then once that stuff happens, something else is going to happen. I know I'm saying very big terms here. Something else is going to happen, and then it's going to take this molecule. All right, you're done. I don't want you anymore. Bye bye. And it's going to float off. And then the cycle will continue. The respiration cycle continues, and somehow, our phosphate group is going to attach with the ADP, and it's going to create ATP once again. So you're probably like, okay, I kind of get the smashing demolition derby thing. I get a little bit about talking about the bond energy here thing. I don't really get what you mean by go do something. I got you back, folks. So a few weeks ago, we talked about this stuff called active transport in the cell membrane. And you might remember that this thing in the active transport, we say, okay, active transport is when we have a concentration gradient where these membrane proteins here are going to allow stuff, and this stuff, to go from an area of low concentration to high concentration, when normally it likes to go from high concentration to low concentration. And we say this requires ATP. Well, let's see how ATP actually works with this, and hopefully make a bit more sense and kind of tie back to those cell membranes, that activity we worked on. So, represented here, I'm using one of the more popular transport proteins. This is called the sodium and potassium pump. The sodium is represented by the symbol Na, and the potassium is represented by the symbol K. In this situation here, in our cells, there's a higher amount of potassium inside of our cells than outside, and a higher amount of sodium outside our cells than inside. So let's kind of see how this thing works here. So let me go over here, and I'm using my models here again. So I just kind of sketched here, kind of showing here that here's where our concentration of sodium is, and here's our kind of concentration of potassium. You skip a little bit. And I'm almost going to say that potassium, let's call our potassium these little green dots here. You can barely see at the bottom. A bunch over there. And we'll call the sodium are these black ones. It's really supposed to be carbon. We'll just call sodium black ones. And just to kind of show how this pump here works a little bit. Well, normally, our sodium potassium pump is chilling and it's open to the inside of the cell. And what happens here is you got this sodium that's just kind of hanging out here on the inside of the cell. It's going to find a nice little spot to snuggle up with and get cozy. And it kind of gets cozy and got sticks there. And it's like, okay, I'm comfortable. I'm taking a nap. Y'all leave me alone. It's going to stay that way. It's going to stay asleep until we do something to it. Well, let's do something to it. Here's ATP. Uh-oh, hits a water molecule. Bam! Breaks off the phosphate ion right now. Phosphate ion comes up and says, you know what? I am going to run into you. It physically smashes into it, folks. And here's our transfer of energy. It physically smashes into this sodium potassium pump. By physically smashing into it, it's going to bind to it for a little bit. And then this pump here is going to make, I don't like this anymore. And it's going to change its shape. This thing's going to change its shape. And change its shape by kind of doing this, like a little alligator mouth here. It's going to completely open up on the other side. And close up the side down here. And now that it changes its shape, it's allowing this open spot right here. It also changes its shape and says, hey, you know what? You get out of bed. You're too much. I can't handle you. And it spits him out. Spits the sodium out, and it spits the sodium out against the concentration gradient. Now there's more sodium over here. Normally it doesn't happen that way. Meanwhile, because hey, that phosphate's still right there. The phosphate's happy, not for long. We got this stuff we got potassium. And it's kind of hard to see with these models, but potassium is almost twice the size of sodium. I mean, it's huge. It's really big. And so potassium now is going to see another part of the pump here. It's going to see a part of this sodium potassium pump, this protein. I can go in, I can latch on right there. Now the potassium is going to be like, hey, it's my turn to get in bed and get all snuggly and comfy. And it's going to get in right there. But when potassium does this, guess what? The protein doesn't like that. It's going to shake and wiggle, and it's going to do this. It's going to close and close and close and close and open to the inside. And when it does that, it changes shape again. And it's going to say, you know what? All y'all get lost. Bye-bye, potassium. Get rid of you. And it's going to take our phosphate right here. Get rid of the phosphate. And while our phosphate is running around trying to find somewhere in the cycle of respiration to kind of join back together to create once again our ATP. And look, it made it. We had seen there how our potassiums went from an area of low concentration to high concentration. So there you have it. This is again, it's kind of a silly explanation. Again, there's so many other videos out there about how to do this. But the big thing, the big thing is, you need to know what is ATP. You don't have to memorize the equation. What is ATP? And the words we like to use is this is kind of like molecular currency. It gives the body energy. And by giving the body energy, it's not like plugging into an outlet or getting gasoline. It's about having that one molecule right there. It gets broken off and it smashes into something else. And when it smashes into something else, things happen. And it's really cool how the cycle just keeps on happening again and again and again. I do hope this video helps, and have a great one.